but generally it's non-zero. In terms of other quantities, what does this mean? What does this imply for the Christoffel symbols and the point of P? Sorry? I think I heard the whole, which was correct. It's zero, right? So that this means that the Christoffel symbols and that point are zero. The Riemann tensor, though, requires second order derivatives. So the Riemann tensor is non-zero generally. At that point, generally. So this means that locally in this sense, in the sense that the first derivative is zero, the second derivative is generally non-zero. So locally one can distinguish if we are in two different, so that this is an example, this is the typical example of the elevator and Einstein's elevator without a gravitational field, by which I mean in flat space-time, like being pulled by an external force, being pulled with an external force, pulling it, or an elevator on the surface of Earth, external force equal to G. G here is the gravitational field of Earth. It's not the metric here. Acceleration. G. Earth's acceleration. So we've got Kz would be your man here looking at some particle. So Kz, is in flat, so you've got an elevator in outer space. There's an external force pulling it. This is external force. And so the guy, the observer in the elevator sees the particle, some particle here going down with an acceleration, G. And in here, you've got your elevator on the surface of Earth. You've got your little observer, and the particle is still going down with the same acceleration. So this is locally, you can't tell the difference, but non-locally, you've got two particles. Oops. Two particles. Both of them with the same acceleration in the case of outer space. And in here, you've got that gravitational force, the force by Earth, is actually pulling the particles towards the center of Earth. Okay, this is a massive exaggeration, of course. This is not at scale, but this would go, it means at the center of Earth. So non-locally, you can tell the difference. This is a tidal force due to Riemann tensor being different from zero in Earth. Yes, one cannot distinguish. Locally, one cannot distinguish. Thank you. Crucial. A crucial knot in there. Just to give you, we're just finishing this. I expect everyone to have seen this in students 11th year. So, just to give you a modus operandi for this, if you've got the conservation of the strength energy tensor in flat spacetime, how do you get, what's the corresponding equation? What's the corresponding equation in car spacetime? Well, as I say, what you do is you write it in a locally invariant frame. Okay, so you could write it replacing the partial derivative by a covariant derivative. This will be true. This will be true in a locally invariant frame in car spacetime. I can go from here to here because the Christoffel is equal to 0. Now, could I do something like this? Could I add something like this? Am I allowed to do this? I can't write this very well. G alpha beta. Let's make it covariant. Well, let's look at this. Am I allowed to do this? By the strong equivalence principle.
No,
Why not?
because it does not have the same tensor form as you had in the
Right. So in the locally invariant frame, so I can do this because the Christoffel symbols are 0. I can't do this because R is not generally 0. So in flat spacetime is equal to this. Obviously, this is also true in flat spacetime. This is the gamma equals 0. In flat spacetime, is the gamma equals 0. For a locally invariant frame, but Riemann is not 0. We want the same form, so I'm not allowed to do this. So this is a strong equivalence principle tells you this. This must be the case. And so you just apply a tensorial transformation to this that tells you that this is true, this form is true. True in any frame in curve space. And you can keep doing this for the laws of physics. Okay, that's the end of revision of classical field theory. Any questions about what we've done so far? Okay, so we're going to grow up as physicists, and we're going to do a bit of quantum field theory. We're going to do it in flat spacetime first. And a lot of the physics in flat spacetime, because of the Green's principle, a lot of things, some aspects carry over to coarse spacetime. So we'll spend a while looking at things in flat spacetime. Okay, so this is the third area, or is it second one, is it? Yeah, just the second one. QFT in flat spacetime. Oh, before we do that, I'm going to set up the framework. I described this in the first lecture. Now we will do a little bit more specific about the semi-classical framework. Okay, so this does not fall within flat spacetime, but this is general coarse spacetime. So semi-classical gravity, if you wish. So I'm going to tell you, I already kind of described this in the first lecture. Doing more formal now. So first of all, we've got a line element, or a metric, given by this. And we've got the anisotropy field equations. We now already know what they are. Already know the right factors of C. And like I said, semi-classical gravity in this framework of semi-classical gravity, we quantize all matter fields, but keep gravity, but keep the gravitational field classical. Okay, so the metric, classical gravitational field will be the metric. Yeah. So plus for the plus sorry? It's a plus. Plus. Sorry. Thank you. What do we mean? So gravitational fields we G. What do we mean that we quantize the matter fields? So instead of the classical Einstein equations, or in the classical Einstein field equations, we replace T mu by the expectation value of the quantum strength energy tensor renormalized when the field, this is psi, is the state, the quantum state of the field. Okay, we still haven't quantized field, but we'll do that at the end. So what we really want to do is you calculate everything, the strength energy tensor and the Ricci tensor and the Ricci scalar in the same metric, G. Okay? You want to solve, this is the holy grail of semi-classical gravity. You want to solve these equations. Okay? As I say, ideally, you want to calculate everything. You want to find the self-consistent solution of these equations. You want to find the G, the metric that satisfies this. I should say renormalization here really means that we're going to renormalize these guys. These radius of G renormalized and a lambda renormalized. We're going to see this a little bit later on the course. Okay. So ideally, solve the semi-constant equations. Self-consistent. And by self-consistent, I mean exactly this. Evaluate the Strensky tensor and the Ricci tensor in the same metric. And the G is exactly the solution of this. But this is very hard to do. So we're going to do an approximation of this. In practice, evaluate T mu on a fixed classical background spacetime. G. And then solve the equations in order to find the back reaction, the quantum back reactant metric. Let's call it G with a superscript of 1. So now this is by the way, this is a short notation for this. I use it sometimes. This superscript sign here just tells you in which state the field, in which quantum state the field is in. Okay, it's the expectation value of this operator in this quantum state. There's a shorthand notation for that. So I'm just writing the full expression for this here. And now T is not evaluated in the G1 metric, but in the background metric G. Okay? That's what we mean by background spacetime. You could say some background spacetime, it doesn't have to be flat spacetime, it could be a curved spacetime, put some matter on it, and evaluate the stress energy tensor for that matter on that background spacetime. You put that on the right hand side of the Einstein equations, and then solve them. Okay? Now, just calculating this for a black hole spacetime is already very hard to do. But if you manage to do that, then the next step would be to do this. You could then solve the full equations here perturbatively. You could then find G1, calculate the stress energy tensor of that G1, find the G2, and keep doing this.
Yeah, we expect G1 dimensional on the G.
Dimensions.
Do we expect G1 be much smaller than G?
Well, G1 is not a perturbation of G. G1 incorporates G and background effects.
So G1 can be written as G plus small piece. The point I want so basically,
Not necessarily, I'll say maybe. I can say yes if that's.
I just wanted to know if, in some sense, one could use a linearized Einstein equation for the perturbation
Yes. Yeah. So yeah.
by
Yes.
the quantum field in that.
Yeah. So yes.
Ish.
To do it, to make sure things are correctly done, yes, that's true. So say, for example, you could do, so we did solve this in 2 plus 1 dimensions. We could solve it analytically for a black hole, we designed black hole. So what we do, you've got your, so the background space-time is this sort of stuff. And then you calculate the stretch energy tensor of this background BT black hole space-time, and then you solve for this. And what we found is you need order, some Planck length correction to that. The reason why I didn't really want to get into this, but the reason why it's not necessarily solved like this is because in here we found things like this. Which is not quite the same. I'm going to, if you expand this for a small LP, that's not quite the same as linearizing GRR. Okay, it's not in reference, but just to make things simple, let's forget about this. To make things simple, yes, you do that. We have justification for doing this, but I can give you an extra justification for this specific case. That's the reason why it doesn't necessarily have to be like this in very particular cases, but in general, as I say here, you go in here, you just solve this. I think actually how we do this in 1 plus 1 dimensions, or things we have a lot of constraints that allow you to do this in 3 plus 1. I'm not aware of anyone.
One see this equation as basically the postulate definition of what's a big probability.
Yeah.
So in a sense, could you somehow derive it from something else? If you don't have a quantum theory of reality, can you still somehow justify why this is the right problem to?
The justification is more heuristic or physical or intuitive, and there's no demonstration of this. We're ignoring, I mean, this is valid in the semi-classical regime. Okay, we're ignoring fluctuation, we're just taking the expectation value here, we're ignoring fluctuation around the expectation value, for example. So some people incorporate that. There's a lot of frameworks in which they're trying to do this. But this in principle, higher order, subdominant to this. This would be closest to classical gravity, if you wish. We're still incorporating quantum mechanics. Okay, so this is really the framework we're in. Okay, we're going to fix some classical background, and then we're really going to calculate these sort of stuff and see what it does. And you get a feel for what a quantum backreactive metric is. So this is what Hawking did, right? He fixed the classical background space-time, which is in that case it's a black hole, charged black hole space-time, and calculates this. And he finds that there's a flux of quantum radiation coming out of Kraglos, which is Hawking radiation. One last thing about the framework. We know from quantum mechanics that there's the Schrödinger picture and the Heisenberg picture, and an interaction between in quantum field theory, we use the Heisenberg picture. So we'll, unless I say otherwise, we shall work in the Heisenberg picture, unless stated otherwise. What this means is that the matter field satisfies a wave field equation, and it also means that the quantum state is just fixed, it does not evolve, so the quantum states are time dependent. So psi in this case. One of the nice things about this is that the field equation, so it gives you the time evolution of the field, but you can write it in a covariant way. Box I will at some stage, so it very naturally captures the covariance of the field. Any questions? Yeah.
If you wanted to use the Schrödinger equation, how would you? There's the Schrödinger picture. How would you? Yeah, I can't even imagine what it would look like.
Yeah, I've never worked. I don't know of anyone working in the Schrödinger picture. KFT. I don't know how you do it. I would, perhaps there's a way of doing it, but that, I don't know.
Because the Schrödinger equation is no longer existing, so you would need another equation to resolve the state.
I mean, that's how the Klein-Gordon equation really came up on the drag. So by trying to, people thought before doing QFT, they were talking about second quantization because they were still thinking quantum mechanical terms of wave functions. And so they tried to come up with a covariant equation for the wave function, and that's how they came up with the Klein-Gordon equation. But it's not, we're not dealing with wave functions anymore. Okay, the field now, you don't think of this as a wave function. Okay. The equivalent of this is the field, the Heisenberg equations of motion in quantum mechanics, if you wish. That's the parallelism you want to establish. This is not a parallelism with the Schrödinger equation for a wave equation, for a wave function in quantum mechanics. This is the way you can think about it. Yeah.
Naively, in quantum mechanics, it's easy to go from Schrödinger picture to Heisenberg or interactive pictures.
Yeah.
What is the feature of quantum field theory that makes it so difficult to work with changing the picture you are working with?
I've never even tried to work with a Schrödinger picture. I'm not even aware of any books that do it. Although I think there's some examples perhaps in cosmology where they do in fact work with interaction picture. And I don't really do cosmology, so I haven't really looked at that. Maybe I'll try to include some cosmology here. But, I mean, the question was, what's the problem with the quantum field theory? I think the main problem is the one that Alex was pointing at. It's the fact that we're dealing here with space-time, and we want things to be covariant, and a natural way of using square. Or the choice of a time, how do you like the time in quantum mechanics, Schrödinger equation? Makes sense. Okay, so we're within this framework, semi-classical framework. So as I said, we're going to start now with classical quantum field theory of flat spacetime. This means that this background G is going to be flat spacetime. So we will consider the background metric G to be fixed and equal to the Minkowski metric. So our space-time is just flat. And in Cartesian coordinates, this. So that's the inverse. It's just the same. And the line element is just minus dt squared plus dx squared, dy squared. Okay, so we're going to do canonical quantization. And we're going to do it for the case that the field, the matter field, is going to be just a real scalar field, just to make things easier. For now, we're just doing it classically, and we're going to quantize in a second, we're going to quantize it. Okay, so for now, so kg tango equation. Okay, the box, the Don-Bersham operator is just this. This is just this. The covariant derivatives in both partial derivatives and the Christoffel symbols. The Christoffel symbols in flat space-time in Cartesian coordinates are 0. So this is just equal to this. And so in Cartesian coordinates, That's just a Laplacian on your Riemannian manifold. And now you can solve this. We're just in flat space now, so this is trivial. You can do separation of variables to solve this PDE, this 3 plus 1 PDE. You can just do separation of variables. Some spatial Fourier transform. The modes, the solutions, you can denote them by UK, and they're just ikx for the Laplacian part of it, and well, it's obvious what the time factor is going to be, but just let me be pedantic if you wish, and just assume that we don't know what it is. X is a product of the manifold, K leaves in R3. And so that just gives you so we apply this, we apply the Klein-Gordon operator onto UK. So from the second time derivative, that's just minus phi x t, second derivative, so a dot denotes derivative with respect to time. From the Laplacian, you just have ik squared, because it's a second derivative, minus m squared. So we want this to be 0. This is just minus k squared. So k is just the absolute value of the vector k. And we want this to be 0. Okay, so this is the second time derivative plus k squared minus m squared. Plus m squared for phi k equal to 0. And let's denote this by omega k squared. Why do we not denote it like that? There's just a simple harmonic oscillator equation. I didn't write this explicitly when we did it, but it follows totally trivially. So remember the simple harmonic oscillator. We did it for A, for the annihilation operator A, but you get the position operator Q by combining A and A dagger. So we did it for A, that was IH dAdt. This was, so these are the Heisenberg equations of motion for the operator H, which is defined in terms of Q and P, position and momentum. This was in quantum mechanics. Okay, so this is, you look at the Hamiltonian of the simple harmonic oscillator, which is H bar omega A, and so if you take the second derivative with respect to time, h bar go away. So this is I h bar ddt of the first order derivative, which is minus I omega A. The I and the minus I go away. So you have h bar omega dA dt. You apply this again. dA dt is minus I omega A. And so this is minus I h bar omega squared A. Okay, the h bar and the h bar go away. The I and the I go away. And so you have second derivative plus omega squared A equals 0. And that's just the same as this. Remember, Q is so that you get the same thing, same for the adjoint of A, gray dagger, and so same for Q. Okay, so Q satisfies the same, same equation as the time-dependent part of the time-dependent factor in the field. Once you notice this, you're done. Okay? You know how to quantize the harmonic oscillator, and so you know you infer from that how to quantize the field. You just look at the field as a bunch of harmonic oscillators, and you quantize each one of them. Okay, so we can write the full solution to the Klein-Boltzmann equation as from the modes. These are mode solutions. Proportional, because I haven't normalized it in any specific way here. We'll look at that in a second. If this proportional factor gives you a factor, this proportionality sign gives you a factor which is independent of the space-time point. So I'm going to include here some factor. I'll justify this later. There's just a normalization we don't really need to care about this for now. Well, the solution of this obviously is phi k. You can write it as a linear combination. Of exponential of plus I omega kt and exponential of minus I omega kt. Okay? Of course, you can choose sines and cosines and so on. Okay, so this, we have this here. Now, we want the field to be real. Remember, we're dealing with a real field, so we need to add this in order to make it real. So this is the convex conjugate of this. So phi real requires that we combine things in this way. Yeah.
I'm not sure I understand your logic. Once you've determined that phi k is a linear combination of exponential I omega kt, you can go back to your ansatz, and then you can go to the left hand side. What was the need to recall the simple harmonic oscillator? I thought you were using the simple harmonic oscillator and justify what you do on the left.
Well, I want to justify what I'm going to do in a minute, but not this. So far, you can ignore simple harmonic oscillator derivation.
Okay, so once you have this linear combination, on the right, you can immediately get to the left by saying that phi is real.
Yeah.
Is that correct?
Yeah. This gives you, from the spectral theorem, this you know that this is a complete set of modes, so that you can write the general solution for the Klein-Gordon equation as a linear combination of these modes. But the reality of the field requires that this combination. So what was did I hand up? Did you have a hand up? So these are the Fourier mode coefficients. This is not the unique way you can write the linear combination, by the way. Because you could write, you could have written a plus here and a minus there, for example. This does not change the physics, so you could do that. It makes zero difference to anything, any physics or anything. What matters is this gives you any general solution, any real valued phi which satisfies the Klein-Gordon equation can be written this way. That's not a unique way in which you can write it. And in fact, we're going to find other ways of writing it. You can do the decomposition in different ways, but the general solution can be written. In particular, you can choose this decomposition. Okay, so let's look at the total energy. This is given by the Hamiltonian. Note that we are in flat space-time, so this T00, you can put the two of them downstairs. So you go back to the expansion that I gave for T median and just look at the 0, component of that. And you find that that's equal to this. So all I'm doing is just taking looking at that expression for the classical stress energy tensor for a real scalar field with a mass, general coupling sign, and looking at the 0 component of that. Okay, so that's equal this. Now, this term here is a total divergence and so by Gauss theorem that will give you zero contribution.
If you do the calculation, you find that the coupling constant is again.
Exactly. So that has the curious bit that even though the strand energy tensor does depend on the coupling constant, the Hamiltonian does not, and the Klein-Bodian equation does not.
Does it happen also for the momentum?
You mean for the other components of the strand energy tensor?
Yes.
I haven't checked. It's a good question. Maybe I did check it. Good question. Okay. So how do we still have to integrate this?
Yeah. So in the first, second, third, fourth term, yep, the one that has grad phi, is it grad phi square?
Phi dot square.
Yeah, and then the one next to it is grad phi square.
Oh, that probably should be the square in the, yeah, the square should be in the inside, right inside. Thank you. So you have to integrate this now. We're just not going to look, we're just going to do in detail the first term. It's quite trivial, but let's do the first term. I'm not going to do the other ones. Okay, so we have to put in all this lot in there. So we're going to have the square of the square root, that's 16 pi cubed, and well, omega k depends on k, so we can't really take it outside the integral. We have the 1/2, we have the integral over space, and now the two integrals over k, and here we have an omega k from one phi, and then another integral with another k primed, and so a square root of omega k primed. Omega k only depends on the modulus of k, the vector k, not on the. And this is integrated over r cubed on r cubed. And now we need to take the derivative, the time derivative of this. So all that means is bring it down a plus minus I omega k. Okay, so it's minus I omega k, ak. from one phi dot, okay, brought down a minus I omega k from this and a plus I omega k from this. It's squared, okay, so we need to include the bit from the other guy, and it's the same with k going to k prime. So it's minus I omega k prime. Same thing, k to k times. And now you use the distributional identity that relates the Dirac delta function, Dirac delta distribution, to integrals of exponentials. Okay, so what do we have? The first term with the first term, that's a plus ik prime plus ik. So I'm bringing in, by the way, I'm bringing in this guy, I'm bringing it in inwards. I'm doing the integration over space first. Okay, so the first guy, we have minus I times minus I, that gives you minus. So it's minus omega k times ak times exponential of minus I omega k plus omega k times t. And we have delta k plus k primes. Okay. Now, you have an exponential of I k times x. But it tells you, the delta here tells you that this only has support where k plus k prime is equal to 0, and so you can just ignore this. And similar for the other terms. So we're doing the first one in here with the second one in here. I don't even put in the exponential with the x in here because it's just equal to 1. Now we're going to do the first one in the first factor with the last one in the last factor. And the last one factor with second factor. Okay. So now that allows us to go through one of the integrals. All these deltas allow us to go through one of the integrals trivially. The first one is just so omega, you'll have omega. This delta tells you that the value, absolute value of the two k's is the same, so this gives you omega k squared. From here, you're going to get an omega k. That's why you have a factor of just one omega k. The minus, k prime is equal to minus k, and then the two omega k's are the same. So that's the first term, and similarly for the other terms. You do the same for the second term and the second term. And you get that the Hamiltonian is equal to this. What system, what physical system is the Hamiltonian of? Harmonic scale. Calcium. So you can really view the field as a combination of decoupled simple harmonic oscillators. For each k, you have a different one with a different frequency. So we quantize it just the same way as we can quantize the harmonic oscillator. The AKs become the annihilation operators for particles for the kth harmonic oscillator. The AK complex conjugate becomes an operator which is the creation operator for the kth harmonic oscillator. And you impose the commutation relations between AK and AK dagger, which are satisfied in the case of the simple harmonic oscillator. So this hat tells you that this is it's an operator and it's the annihilation operator for the case harmonic oscillator. And the AK complex conjugate becomes creation that's all you do, and you impose the commutation relations. Okay, so all you quantize is these are Fourier coefficients, and that immediately leads you to the field phi being an operator as well. This immediately tells you that phi becomes an operator given by this. The UKs are mode solutions of the Klein-Gordon equation, and I gave a proportionality factor at the start. Now I'm choosing the proportionality factor to absorb this here. I'm going to justify it on why that's what we want. But so far, I just defined the mode solutions with this factor included. So this is your quantized field. Now, a crucial thing is these guys now are operators, so generally they do not commute, and the commutation relations are given by the commutation relations that we found for the harmonic oscillator. So you want to impose this and they're decoupled. So this so the A's obviously commute and the A daggers commute as well. These are the commutation relations. And that's it. That's how you quantize your field.
dependency of the quantum field, which evolves in the picture, is only through the functions UK. The operator-like nature being the coefficients, which are just constants. It's just that they don't commute, but they don't evolve in space and time.
That's right.
And that's going to be true for every field in general?
Yeah. For every field, then it's based coarse space and so on.
Can you repeat the question?
So I was asking Mark if it's correct that the field phi, the scalar field, viewed as an operator, is depends on space and time, evolves only through the functions uk of x, which are not operators, and the operator-like nature of phi is encoded only in the coefficients ak and ak diagram.
Thanks.
Actually, is it AK? Is it
Oh,
part AK and AK dagger?
oh. Thank you. Now, mathematically, there's a lot of subtleties. And in order to make this rigorous mathematically, we haven't really done this, and I'm not really going to get into this, but I will just skim over a few of the issues. So there's other ways of quantizing the field which are more formal, more mathematically rigorous, and so on. Algebra and QFT is probably. Okay, but I'm not going to get into that. We're not doing foundations of QFT or mathematical QFT. But you do have to be aware of quite a few issues. First question is, I'm saying that AK is an operator. Okay. So my question is, you look at these computation relations, and I ask you, is it really an operator? So what is it if it's not an operator?
There is a distribution in the computation relations.
Sorry?
There is a distribution during the computation relations.
Right. So what is it if it's not an operator?
Distribution.
It's an operator valued distribution. So that means is, if you have an operator and you apply it onto a test function, if you smear it with a test function, you get a complex value. If you smear this with test function, you get distribution. So this is a distribution. One is that is the unit operator, of course. And so phi is an operator value distribution. So in other words, phi is not well defined as an operator. Operator, I abbreviate it as OP. this is a well-defined operator. I don't know what I said before. I think I said something wrong. I think I said the operator acting on a smear with a test function gives you a complex value. That's not that. And you can take the expectation value of an operator and then you would get a complex value. It's when you, in here we need to smear it first. We need to act on a test function, then apply the expectation value to get that. So this is a well-defined operator. So phi is a distribution, or it's an operator value distribution in this sense. We need to smear it first to get an operator. Because
this focus, because phi is made of A and A dagger, and what is a distribution for sure is a commutation of A and A dagger. But couldn't A and A dagger themselves separately not be distributions and their commutator be a distribution? Is that possible?
we should struggle to see how that will be the case. We have products. So I don't see how that would be the case, but I can't prove it that that's not possible. So as I say, things like phi expectation values of phi. Now they're not. It's not a complex number. It's a distribution. But if you smear phi with a test function first, that's a complex value. We are not going to get bogged down with this sort of stuff. Okay, we're not. It's worth being aware of this. But this is not going to interfere with our calculations.
So does it mean that the stress energy tensor scalar field will be a distribution, and then the Einstein equation itself needs to be interpreted in a distributional sense?
Right, so yes. So, well, let me see. So, there's all sorts of funny things happening. Well, so So that really is at the heart of renormalization as well. So I would say that after renormalizing, that's the issue why, so the static tensor is then products of distributions, which is not really well defined. And this is at the basis of the renormalization. But after renormalizing, I think we're good.
So after normalization, we have something which is well defined, but is that thing which is well defined still distribution or?
I don't think so. I think that's it's a distribution which is a function, basically. Not distribution which are just functions. Standard function. You can think of standard distribution. So I think that's defined as a function after the normalization.
So you have an ordinary right hand side.
Okay, the next thing is to build. So we have a Hilbert space in the quantum mechanics. We want to build a Hilbert space. We want to know what the Hilbert space is for this, for the quantum field theory, and what the inner product is. So we call positive frequency solutions. When I say solutions, I mean solutions of the Klein-Borg division. Of the Klein-Borg division. Those solutions fine. There's 40 modes. Fourier transform. Is 0 for all omega. So just you can look at this just in terms of the classical. We're just looking at the classical space of solutions. That's why I'm not putting a phi hat here. It's just the UK's, like Alex pointed out, the UK's, the solutions of the Klein-Borg equation are just, they're not operators. So in particular, the UK that we defined are positive frequency modes. Since omega k is positive. Okay, all you get is you do this integral here. You're going to get a delta of omega minus omega k. And so, unless omega is equal to omega k, that's going to be 0. And omega k is positive anyway. So this is going to be, this integral, this Fourier transform is going to be 0 for all omega negative. So the UK's, I mentioned this before, which is writing it, is the basis of the vector space, I'll call it P, of positive frequency modes. the UK stars is the basis